I'm delighted to be here speaking at the Sustainability and Climate Action event. So yes, my name is Simon Philbin, and I work as the director of the Nathu Puri Institute for Engineering and Enterprise at LSBU, and I also currently serve as the president of the American Society for Engineering Management. And the title of the presentation is Towards Environmental Sustainability Through Engineering Management. Well, first of all then, why is environmental sustainability important? Well, we know that there's been a definition of sustainable development since the late 80s, the famous Brundtland report. But I've also pulled out a definition here, a more recent definition. And it says environmental sustainability defines a boundary for us to satisfy our current needs without any way compromising the quality of the environment or the ecosystem, so that it remains equally capable of supporting the future generations too. So in common with the Brundtland definition, we have the focus on protecting and maintaining the situation for future generations, but clearly we have a focus on the environment and the need to avoid compromising it and protecting it. But what about the case then of global temperature and climate change? Well, there's a lot of evidence now to suggest that the increasing levels of carbon dioxide in the atmosphere caused by the burning of fossil fuels is unfortunately resulting in an increase in the global average temperature through the greenhouse gas effect. And this data is a few years old now, but we can already see that by the early 2000s, we'd seen about a 0.6 degrees Celsius increase in global temperature. And I looked it up this morning on the NASA website, and it's now about just under 1 degree, 0.95 degrees odd increase from the long-term average. So we would say that the burning of fossil fuels and the carbon dioxide being released, that is not environmentally sustainable, clearly. Now, efforts have been put in place to try and limit global warming. There is the widely known Paris conference of 2015, where 195 countries adopted a legally binding agreement, and that was to try and limit global warming to 2 degrees. And you can see a chart there, which is mapping out a number of trajections or profiles to try and reduce the annual amount of carbon dioxide released from burning of hydrocarbons, which around 2010 was around 50 gigatons per annum. And so some quite dramatic reductions are required in order to try and limit it to 2 degrees. But in 2018, the Intergovernmental Panel on Climate Change released a further report to say that actually we need to be putting in place steps to make that, to limit the increase to just 1.5 degrees. So there's a lot of work to be done. Now, what I wanted to do really is to use engineering management as a lens to focus in on environmental sustainability and to consider some carbon reduction strategies. Engineering management is concerned with the management of people and projects in a technological or engineering systems context. And it also provides a range of tools and techniques for analyzing complex situations. In terms of the research strategy then, it was to focus in on 2 potential approaches to reduce carbon dioxide levels. That's the adoption of electric vehicles and something called carbon capture and storage. And a technique was used called techno-economic analysis, which is a way of analyzing complex situations through considering the technological and the economic factors, and then synthesizing evidence-based findings based on the available data. And this work was published with collaborators in different journals last year. First of all then, looking at the case of electric vehicles. Well, we know there is an increasing prevalence of electric vehicles on the road, and battery technology is improving, but there are a number of challenges. Battery life itself, the time for charging, availability of charging infrastructure, costs, and other issues. So a techno-economic analysis was designed to focus in on economic modeling and some key review of technological areas. One of the first things we did was a benchmarking exercise of economic data on different types of vehicles. We looked at 31 vehicles, and there were 7 electric vehicles, 7 hybrids, 12 gasoline or petrol vehicles, and 5 diesel. This study was focused on data from North America, so we captured the retail price from California and the EPA energy consumption rates. And for example, we captured data on the Nissan Leaf electric vehicle and the Toyota Prius hybrid, a Cadillac Escalade, a gasoline petrol powered, and a Chevy Cruze diesel vehicle. So we captured this data, and one of the first things we did was charted some of that key data. And the graph on the left is charting curb weight with the recommended retail price. Now, interestingly, generally, curb weight, the weight of a vehicle, is correlated with the cost. So a heavier vehicle will tend to cost more. But for the same size vehicle, an electric vehicle will tend to cost more than say a gasoline or a diesel vehicle. But there is some spread in the data, so generalizations can be not always straightforward. The graph on the right is plotting curb weight with fuel economy. Now, not surprisingly, electric vehicles have a higher fuel economy of the different types we're looking at. But it's worth noting that where coal or natural gas is being combusted to generate the electricity, then the inefficiency, I should say, of that energy conversion is not included in the miles per gallon for electric vehicles. So you don't get a full story with that picture. It depends on where the electricity is coming from, the full life cycle of the energy usage. We also did some economic modeling of annual vehicle costs by fuel type and developed a model based on a series of assumptions. For example, we used 10% of the purchase price of the vehicle as the annualized cost of capital. When we did this modeling, again, we found that electric vehicles are quite a lot more expensive, coming just under $5,000 per annum, whereas a gasoline vehicle at just over $3,000 per annum. Because with an electric vehicle, you've got a contribution towards the replacement of a battery. Battery life is not usually as long as the vehicle life. You've got a higher capital cost. Now, with the technology learning curve, we would expect that technologies being available for a longer time frame, such as a petrol-powered vehicle, would cost less anyway. But nevertheless, it's interesting to see how much more expensive an electric vehicle is to operate. We also did some trend estimation on the availability of electric vehicle chargers, which is one of the factors holding back the adoption of electric vehicles. And we can see from this modeling based on International Energy Agency data that we expect the availability of chargers to pick up quite dramatically. And so this will be less of a factor holding back electric vehicles in the future. We also reviewed some data on the environmental challenges. This is data from a published source by Zhu et al. And we were looking here, considering the situation, what happens with the recycling or the disposal of the lithium-ion batteries in electric vehicles. And there are challenges because of the sheer range and diversity of the components in the batteries. So you have metallic-based components as well as non-metallic, and it's quite difficult to recycle all of them. And unfortunately, a hazard of electric vehicles may be that a lot of batteries are just going to be sent to landfill, which again is not environmentally sustainable. There are also economic challenges around recycling batteries. So, for example, when the cost of a component material is high, compared to the value of the cathode in the battery, such as in this chart, component A, then the viability of recycling is much higher. And that this is data from Gaines, the author. Whereas when a component, the bar in blue is much lower than the bar in orange, then the value of the cathode is much lower. And in that case, there would be a lower incentive, a lower economic incentive to recycle. So we can see that there are technological challenges of recycling batteries and also economic issues to deal with there in regard to electric vehicles. Well, that was the first part of the study. The second part was to focus in on the other area, which was carbon capture and storage, so-called CCS. Now, CCS involves capturing carbon dioxide from waste streams and then pressurizing it and transporting it to deep underground geological formations for long-term storage. And it's a way of clearly reducing CO2 waste streams or even taking CO2 out of the atmosphere. CCS has been used for many years as part of enhanced oil recovery, but it's not being used on a very large scale for the purposes of actually mitigating the impact of climate change. So it's still a technology under development, and we designed again our techno-economic analysis to look at different factors. Now, there's quite a lot going on with this slide, and it's just to give you a flavor for the technologies here. So the main capture technologies are based on so-called post-combustion, pre-combustion, and oxy-fuel, and each have their own technological issues and areas under development. So, for example, there's new solvents being developed for post-combustion. Pre-combustion, they're looking at different types of membranes based on polymers and ceramics and other materials. You can also capture CO2 from industrial processes as well. But nevertheless, this is an area under development, a lot of technologies and research being conducted. But in terms of the project level, if you were to actually develop one of these large-scale CCS facilities and build it at a power plant, the project itself would be potentially a mega project. It would be a multi-billion-dollar project. So there are issues around how you fund that. Is it government or private? Do you have to think about some kind of tax credit or risk-tolerant loan? And this is work by Jenkins, who looked at this case a few years ago. You've also got to consider how you're going to scale up the capture technology and think about new industrial supply chains. One of the things we did as part of the study is we conducted a comprehensive literature review, and we identified 12 main areas of CCS research, and we grouped them according to technological factors, economic factors, and regulatory and environmental factors. Then we did a further search using the Science Direct online database, and we looked for the frequency of these terms. We found that the areas receiving most attention in the literature, receiving most research, are the development of new capture technologies, new storage technologies, and the need to reduce the cost of this overall technology. You can see that in the chart there. But there are other areas as well, so investment decisions, environmental assessment, the need for new regulatory framework, and other areas are also being researched. But nevertheless, we can see, where the main focus of the researchers is today. We also did some modeling and gathered data on based on a modeling approach using something called the levelized cost of electricity, the LCOE. And LCOE it's a numerical measure that's calculated in order to assess the commercial case for different types of power generation technologies. And essentially, it calculates the present value of the costs for that particular method of producing power per unit of electricity that is generated over the life of a specific power plant. And there is a formula that's used behind to work up to calculate the data. So we did some modeling, but first of all, we also reviewed some existing data, and this was produced by the Global CCS Institute. And they looked at this levelized cost of electricity, the LCOE, for different types of power generation. And they also looked at cases where you would add CCS, where you would add the ability to remove carbon dioxide. So for normal natural gas, it has an LCOE of about $55 per megawatt hour. Adding CCS potentially adds around a $30 per megawatt hour premium to a natural gas powered station. But what we can also see that there are some forms of renewables, such as wind offshore, solar PV, and solar photovoltaics and solar thermal, which are actually a lot more expensive than even when we add CCS to natural gas, or even CCS to coal in some cases. And we can see then that there is potentially an economic case to add CCS to a power station burning, say, natural gas. And we gathered some data on this example further and did some modeling, and we looked at the case of something called a new technology called a combined cycle gas turbine, which is basically a way of generating electricity through a gas turbine, and then the waste heat is used to create steam, which then drives a secondary turbine, increasing the overall power efficiency and power output of the station. And these stations are being developed at the moment. So we gathered data on this type of power station, and we modeled it, and we looked at the case of a normal CCJ and a CCGT, I should say, with carbon capture and storage. And we can see the LCOE, that levelized cost of electricity, falling over the years from between 2012 and 2022. Indeed, the case with CCS added in 2022 is potentially the same cost as the power generation system without CCS back in 2012. So this data indicates there would be assumptions behind this data, but it indicates that we do see an improving economic case for the adoption of CCS as a carbon reduction technology. We also gathered analyzed some other data. I won't go into this in much detail. And for example, we looked at where are the current pilot scale facilities being developed across the world, and the leading countries at the moment are the US and China, and then there are some countries, including the UK, also developing small scale projects in this area. But the development of large scale CCS facilities is still under development. Okay, just bringing the presentation to an end then. So in terms of final remarks, we know that there is an urgent need to implement new technologies at a large scale in order to reduce, obviously, the burning of hydrocarbons and reduce the level of CO2 emissions. Mitigating the impact of climate change is clearly an urgent matter that has to be addressed. Electric vehicles do have a role to play, but there are continuing challenges to be tackled. For example, around the environmental disposal of batteries and the economic factors as well. CCS, carbon captured storage, has potential utility to reduce carbon dioxide emissions, potentially could sit well alongside other forms of power generation as well. So a CCS fitted to a natural gas powered station, and then also we can see development of renewables, and potentially that's part of a multiplicity, a range of different forms of power generation, a range of different energy sources. And hopefully I've also demonstrated how engineering management can be used as a useful lens to focus in on those technology and economic factors to be considered for these different types of options towards environmental sustainability. I also wanted to just put up details of a special issue that we currently have out in the journal called Sustainability, and I'd be delighted to see submissions if anybody is interested to this special issue. The deadline is the 30th of November, and the theme is driving sustainability through engineering management and systems engineering. I'd like to thank my collaborators for the two studies, Dr. Donald Kennedy, who's a researcher from industry in Edmonton, Canada, and Dr. Steve Wang from Sichuan University Pittsburgh Institute in China. And thank you for listening to this presentation on the webinar. Delighted to give it today. I'd also like to point out that my team, the Nathu Puri Institute, we actually have a webinar coming up next week. And if people are interested, they could just Google Enabling Enterprising Engineers. That's the name of our webinar, and they would find the Eventbrite, and they'd be able to register for that webinar as well if they want to learn more about our work within the Nathu Puri Institute. And hopefully we've still got 5 minutes or so for Q&A.
Thank you so much, Simon. That was fantastic. And I actually put a link to the webinar next Wednesday in the chat box. So if people want to join,
thanks, Neil.
Go there. Fantastic. Thanks so much. We've got one question come in, but I just want to say electric vehicles is a really, really kind of like current topic and stuff. I was chatting to someone from the UK Power Networks, obviously one of our neighbours in Elephant and Castle, and they were saying about some of the kind of like implications that people haven't taken into account with them, such as I think they did a trial of them. I think he said in Richmond, and it knocked all the grids out while they were doing it. So there are things that people kind of are not considering when they promote them so heavily.
Absolutely, there are a number of challenges, and we've not been there recently, you know, with the lockdown, but occasionally we would go to Blue Water, the shopping centre, and there are some Tesla charging bays. I don't know if you've been to Blue Water, you know, out in Kent. And, you know, Blue Water is a very large shopping centre, but when you go there, you only count about 4 or 5 Tesla charging bays, and there must be thousands of vehicles going there every day. And yes, I mean the need for the upgrade of the infrastructure is an enormous challenge potentially, and will inevitably require a massive level of investment. But I mean, they are clearly coming along, and they're coming along fast. And you know, companies like Tesla are, you know, real trailblazers in this area, and we're seeing the other manufacturers, you know, increasingly all of them have an electric vehicle, and they will have a hybrid available. I think some manufacturers have committed to go fully electric within a number of years. But you essentially have the kind of catch up then. So as you say, the infrastructure has to catch up. And yeah, other challenges as well. Still a need to extend the life of the batteries, but again, that is improving all the time. So they're coming along fast, but there are still areas to be tackled.
Thank you. Actually, we asked all of our speakers to submit some key messages, some mythbusters and practical takeaways. And this didn't come up on yours, but it came up on one of the other ones around electric vehicles and the fact that they can travel a lot further than people think they can.
Right. Well, I guess, yeah, there are different messages there. I mean, certainly several years ago, there were people saying, well, the stated range of the vehicle was a lot higher than what people were actually observing. Now, maybe work has been done to address that. And it also depends on how you drive the vehicle. If you accelerate very hard, then, yeah, the range will go down dramatically.
I think I've just got the myth in front of me now. It says, you can't travel very far in electric vehicle. Generally, electric vehicles can travel between 150 and 300 miles before they need charging. So that was an interesting fact that I didn't know about. So it's a learning curve.
Absolutely, yes. And for some people, 150 miles will be plenty. If they're an urban dweller, that's perfectly fine. But if you want to visit your relatives up in the north of England or something, or wherever, then that clearly is not far enough, is it?
No, exactly. And we're going to go to some questions from our audience now. Sheila would like to know, in the use of gas and CCS, has the cost of drilling for transport damage to the environment being considered? In addition, why depend on a technology that is not fully developed when the solutions to global warming are already there?
Well, it's a good question. So the use of carbon dioxide and pumping it into existing oil wells has actually been done for 20, 30 years more or more. And it's used for something called enhanced oil recovery. Now, it's not necessarily sustainable. That it's basically you have a certain recovery rate from an oil well. If you pump more CO2 down, it increases the pressure, and you can actually, have more oil and gas coming up. So that side of it has been used. They've modeled that the CO2 would actually potentially stay down there many, many thousands of years, if not even longer. Now, people have also considered that CCS is one of the technology solutions that could sit alongside other steps to reduce carbon dioxide. So, relying on solar panels and wind, they're great technologies, very, very clean. But it's not always windy, and it doesn't always shine, strong sun. So we need to have other forms of power generation that are available that when it's not windy or when it's not very strong sun. And for example, a natural gas powered power station fitted with CCS would be a clean option, then a complement that could sit alongside, say, solar panels. And increasingly we see evidence to say that we need this kind of multiplicity of energy sources. We can't rely on just one. We need to have, because some have pros and cons, as I said, but absolutely we need further development of renewables. CCS is potentially a complement that can sit alongside that.
Thank you. Thomas says, we heard yesterday wind is now cheaper than coal. Do you think economies of scale will make electric cars cheaper over time? And is there opportunity for a circular economy for the lithium batteries?
Good questions. And yes, for taking the second one first, the circular economy for lithium ion batteries. I remember going to a presentation in China a few years ago, and the gentleman speaking there was talking about urban mining of electronic equipment, including batteries, in also basically to get the rare earth metals out of that. So yes, we do need to see more recycling of those materials. But as I mentioned, there are scientific challenges. If you've got a range of different components and the technology that you use to try and recycle, sometimes you might leach out or dissolve so-called non-metallics, so you can recover the metallics, but you then end up, some of the other materials you cannot recycle. So there are still challenges trying to be able to recycle all the components. On the other point, yes, I think as there is long-standing data to show that as technology undergoes something called the learning curve, then costs do go down. So the cost of solar panels, photovoltaics, it's been known historically to reduce significantly. And we can often see other technologies will go through that cycle. So potentially, yes, we will see electric vehicles become cheaper as the technology, as we learn from the technology and there is a greater adoption. Yes.
Thank you. And we're almost out of time, actually. We've got a couple of comments in there. So Chris has put, from discussions I've had with UK Power Networks, the infrastructure in this area will not be able to cope with the electric powered vehicles and the increased demands from degassing for zero 2050. Sunil put EVs charged with grid power, which is not green, and which is better in terms of carbon reduction, use gasoline or grid power?
Well, it depends clearly where the grid power is coming from. If the grid power is coming from the burning of in a coal-fired power station, then that is not good. The end-to-end overall life cycle analysis is not good there. But if the electricity is generated from a renewable form, biomass, it could be a natural gas-fired power station fitted with CCS, then the electric vehicle is very clean. But there is more work to be done on the full life cycle analysis, they call it, of these electric vehicles. And you also have other factors, whereas as a lot of the environmental impact of a vehicle is simply buying the new vehicle. So if lots of people trade in a perfectly decent, still running petrol vehicle to all get a new electric vehicle, there's actually a big environmental impact of simply buying a new vehicle. So there are different factors. So it's a kind of systems view that we need to consider there. But undoubtedly, there's a lot to offer with electric vehicles, but still challenges there to be tackled.
Brilliant. Simon, thank you so much for joining us this morning. There's a few outstanding comments and questions, so please feel free to have a look at those. And another plug for your event next week. I'll put that in.
Thanks a lot. It's been a pleasure to speak at the conference today. Thank you.
Thanks for joining us. Cheers, Simon.
Cheers. Thank you.